Okay, sixth grade. Today we're going to start our talks about earthquakes. We started this PowerPoint in class today, but I'm going to review the part we went over real quick, and then we're going to touch on a couple of new things to prepare for our activity that we're going to be doing in class tomorrow. First of all, we talked real quickly about earthquakes, which is seismology is the study of earthquakes. So a seismologist would be somebody who studies earthquakes. We also touched on what an earthquake actually is. An earthquake is a slip on a fault, and that results in the ground shaking and the energy being released or radiated from that point is caused by the slip. Some volcanic or magnetic type activity can cause an earthquake, and sudden stress changes in the earth can cause an earthquake. Most earthquakes occur along the boundaries of where tectonic plates meet. If you look at a map of the tectonic plates, all along those borders are where most earthquakes, not all, but most earthquakes actually occur. Okay, review of the three types of faults that can cause earthquakes. First of all, there's the strike-slip fault, which is along transform boundaries, where actually the plates slide past each other. Okay, one's going to go that way, the other's going to go this way, and stress builds up in between the boundaries there. That's a strike-slip fault at a transform boundary. Second one is a normal fault, and a normal fault occurs at divergent boundaries. That means, remember that the plates are moving apart from one another, so what ends up happening because of this, along the fault that was produced from the deformation of the rock because of the divergent boundary, is the hanging wall here actually slides downward, whereas the footwall goes upward this way. So that's a normal fault, and then a reverse or a thrust fault is kind of the opposite of a normal fault in the fact that the hanging wall moves upward or is pushed upward, and the footwall here gets pushed downward like that. Okay, so again, what causes earthquakes? Tectonic plates move past each other, causing stress. Okay, when those plates move past each other, stress causes the rock to deform. That's called deformation. And there's two types of deformation. There's plastic deformation and elastic deformation. Now, plastic deformation, usually what the stress does is it causes rock to fold. It's kind of like plastic. It kind of folds or bends. And this will not cause an earthquake. Now, elastic deformation, on the other hand, is where rock gets stressed. That type of stress is called tension. And then the rock reaches a breaking point and energy is released. Now, that energy that is released is in the form of waves. It's not heat energy. It's not chemical energy. It's not electrical energy. It's seismic waves. The energy in the form of seismic waves. And we'll talk about the waves here in a minute. So elastic rebound is where deformed rock goes back to its original shape and eventually released and traveled in seismic waves. Okay, so this shows kind of an example of how that release of stress, the tension builds up and then it breaks at the fault. Okay, so let's talk about where earthquakes occur. The point inside the earth on the fault where the earthquake begins, in other words, where that breakage occurs, where that energy radiates from and is released from in the Earth's crust, is called the focus. That's where the earthquake actually happened. Now, the epicenter is the area on the surface of the Earth above the focus. So like if there was Oklahoma City right here, the focus would be right underneath it if Oklahoma City was the epicenter. Okay, so remember the difference between focus and epicenter. Okay, today we talked about how a seismograph works. And basically what it does is it records the amount of energy in those waves that has been released. So the greater strength of the earthquake, the greater the waves, and then the seismograph, the instrument, will measure a greater wave strength. And we made a seismograph in class to kind of get an idea of how it works. Now, what the seismograph gives you is a print of these waves, and it's called a seismogram. Okay, so a typical seismogram will look like this. The waves, the paper's going through, so this is the first part of the earthquake right here. So this is the earliest waves to hit, and then as time goes on, these waves hit later, and then here's the end of the earthquake. Right there. Okay, so let's go back and talk about the waves really quickly. Primary waves, there's two types of waves in an earthquake. There's primary, or what we call P waves. Okay, now P waves are sometimes called compression waves. Now these P or compression waves are movement, compression waves are caused, I'm getting used to writing with this computer here, but the compression waves are caused when the energy or the seismic waves that are released from the earthquake that cause the particles in the rock to move or vibrate in a back and forth direction. Okay, that's why they're called compression waves. It's kind of like if you have gelatin, a bowl of Jell-O, and you tap at it, well, the Jell-O seems to vibrate back and forth and go back to its original position. And that's the way compression waves work. Okay, it's kind of like a slinky as well. The particles vibrate back and forth and go back to their original position, and they travel as such as well. So from the focus of the earthquake, these waves vibrate or rock move back and forth direction. Now the particles in the crust don't move, but the energy does move and it travels. Kind of vibrates through the particles. It's kind of like when you see people in a stadium do the wave. Okay, the wave moves, but the people stay in the same position. So the particles in their crust stay in the same position, but they vibrate back and forth, causing kind of like a domino effect that moves that energy from the focus on through the crust. So that's a primary or compression wave. So it compresses and expands the ground. So the energy travels that way. Now, primary waves, hence the name primary, are the fastest waves. They're the first waves that come out of an earthquake. Secondary waves, the next type of wave, are sometimes called transverse waves. Okay, and these are typical, if you can picture the waves of an ocean. begin transverse. So they transverse across. So they're like the waves of the ocean. They go up and down. So they move in a side-to-side direction. Imagine having a slinky on the floor, and you and your partner here just shaking that slinky back and forth. You would get a wave-type motion. So the rock would move or vibrate in a back and forth direction. So they travel transversely instead of in a back and forth type like the compression waves do. So these are slower. The secondary waves are slower. They follow the primary waves in an earthquake. So it moves the ground up and down or side to side instead of compressing it back and forth. Okay, so let's compare the two. You've got the primary wave, the secondary wave characteristics, and then both. Okay, primary waves, they travel through liquids and solids. They push and pull. They go about 8 kilometers per second. That's pretty quick. Think about traveling 8 kilometers per second. And cause the first movement you feel in an earthquake. Okay, so the secondary waves, remember the transverse waves, they only go through solids. So these aren't going to travel through liquid. They cause the rocks to vibrate up and down and sideways, okay, instead of back and forth. And they're a lot slower. They go about 4.5 kilometers per second. And these usually cause more building damage. Okay, now they both originate from the same focus and begin at the same time. And they both can be felt at the Earth's surface. Okay, so we got these two waves that rock and roll the Earth coming from the breaking of the release of the stress at the focus. Okay, there's a third type called surface waves. And they move along the Earth's surface and the upper crust. So these are like the shake them up and down and everywhere waves. They're the slowest, but they are also the most destructive because they are more at the surface where we have buildings and rocks and structures like that. So surface waves are slowest, and they go in all the directions, up and down, transverse, and all that. And they cause the most damage because they are on the surface. So the three main types of waves, again, are primary, which are the compression, secondary, which are the transverse, and then the surface waves. Okay, now this is what we're going to do in class. We're going to be like seismologists, and we're going to calculate how far a location is from the epicenter of an earthquake. So we're going to take seismogram data, looking at the P waves and the S waves and their arrival times to a particular seismograph station, and be able to calculate exactly where that focus or the epicenter of the earthquake is. Okay, so one rule as far as being able to do this is the further away an earthquake is from a seismograph station, the greater the time is going to be between the arrival of the P waves and the S waves. Remember, the P waves are the fastest and get to a seismograph station first. The S waves are the slowest, so they're going to get there second. So we're going to calculate the difference in time between the arrival of the P and the S waves, and from that we're going to be able to locate where these earthquakes actually occur. So in looking at that, here is a seismograph station here in Lamont. I'm not sure what state that's in, but they calculated by looking at the difference in time between the two waves, they calculated that the earthquake is this many kilometers in radius from this seismograph station. Okay, and we'll have more details on how we do that tomorrow in class. Okay, Rio de Janeiro down here, their seismograph station also picked up that earthquake. And through the calculations, the difference in time between the P and the S waves from this location, okay, they calculated it's this many kilometers from here to here, radius. So they draw a circle around there, that many kilometers from there. So you see the intersection here between the two seismograph stations is right here. So the earthquake, or the epicenter, or the focus of the earthquake, had to have occurred in between here. So how do we figure out? That's a pretty big area. Well, you get a third set of data there. And here's Berkeley. Berkeley seismograph station felt the earthquake too. They found the difference in time between the arrival of the P wave and the S wave. Went through some calculations and figured out that that epicenter or focus is this distance in diameter, or radius actually, from the earthquake. So the three seismograph stations, the radius circles that they drew around there, all intersect at one point. And that point where all three intersect, right here, is actually where that focus, or that epicenter, or where that earthquake occurred. Right there at that point, where you have to have three seismograph stations and the data from the P and the S waves to actually figure out where an earthquake occurred. Okay, if you just have one, like here at Lamont, they're getting this seismogram, this P and S wave data, but they can calculate the time difference between the two, but they have no idea where along that distance it is. Is it up here, here? So they have to get data from other stations to actually figure out the exact location, which is somewhere over here in Chile, or don't know my geography, but it's over here somewhere. So tomorrow we are going to actually get some earthquake data, P and S wave data, and draw some circles on maps and do some calculations and figure out how seismologists actually locate earthquakes.